Go to the course web page and open Lab 2 that describes the problem. Notice the differential equation, second order linear. Then open MATLAB. At the command line, type Simulink. That will start the Simulink toolbox. Then start a new model. The new model will be typed into this page. These are the common model elements. Drag in two gains. We'll adjust them later. Then a summing junction. And two integrators. On the sources page, grab the step function. Make the summing junction have four inputs, a negative and a positive and two negatives, three inputs. Rotate that 180 degrees. There's a better way to do it. Just click on the one you want to rotate and type Control R 2 times. Now to connect the wires. Just click and drop is one way. Click, release. There's a shortcut way to do it. I think I use click and release for all of these, and they can be wired backwards or forwards. These wires carry the signals from one model block to the other. That signal is going to be x double dot, or the second derivative of x with respect to time. Integrate it once, and that signal is the first derivative of x with respect to time, and that signal is x. That is the solution of the differential equation, that signal. Now we want to feed back x dot with a negative sign. We want to feed back x with a negative sign. If you don't like it, just hit the delete and it will delete it. You can redraw it. Now the gains are 0.4 and 10. 0.4 multiplies x dot and 10 multiplies x. So this one needs to be 0.4. And this one needs to be 10. The step function needs to begin at t equals 0 and the step size is 1. We're going to send to the workspace each of those variables. Since that variable is x, we'll call it x, and it needs to be an array, not a structure. That signal is x dot. We'll call it x dot. Control C to copy, Control V to paste it. It's one way to do it. And that signal is x double dot, so we'll call it x dot dot. We could copy and paste that way. Now there's not room, so I'll grab them all, drag them down, make room for that variable at the top. That's the forcing function. In our equation, we call it f. So I'll name it f. These variables are arbitrary, but might as well use the same variables that are listed in the lab. Okay, present working directory shows that this command window is somewhere else. We want to move the command window to the temp directory on the C drive, or some directory on your flash drive. And then dir will show the contents of that directory. We're going to save a couple of files. At this point, everything we save or create will go into that directory. We'll save this model and give it a name. Don't use spaces in file names. I give it some meaningful file name. That's our Simulink model. That's the name I chose for it. And there's the name that I chose. It's now a file which can be opened later. Whose shows what's in the workspace. I've cleared out the workspace. There I save the model again. Now run the model. The model ran with default parameters. Type whose, you see those variable names that I chose, they now are vectors with 57 elements each one. And if I plot t out versus x, that's the solution of the differential equation over a 10-second period. I'd like a few more data points and also to run the simulation to 20 seconds rather than 10 seconds. So I'll fix the step size, and the step size of 0.1 will give us 200 data points in that 20-second period. Save it, run the simulation again. Type whose, you see there's 200 data points in each of those vectors, and when I plot t out versus x, I get a little bit smoother plot. Now I'm going to write a script. All of the MATLAB commands are going to go into this script. It's really a MATLAB program, so that I can iteratively modify the program and test it, modify it again and test it. I don't have to retype commands that I've typed before. This first line begins with a %. That makes this whole line a comment. It's good to identify the script with some comments. Good to identify the author, the date, the course. Now there's the first MATLAB command that I've already used. It's plot t out, comma, x. I'm going to save this script. I'll pick some script name. Has to start with a letter. No spaces, and then run the script. So really all it did was execute that first line. Now I can add more commands like xlabel. Every plot has to have an x-axis label and a y-axis label and a title. So there's the x-axis label. As soon as I run the script, then those two commands will execute. Add another command to plot the y-axis label. Since x doesn't have any units, I'll just put unit as the unit. So the vertical axis is x. And the grid command will draw a grid. The title command will allow a title to be written on the plot. And the title should also document what the plot is about, the author of the plot, date of the plot, the course, all that information. You'll be printing out this page to submit in your informal lab report. So when you run that script again, it executes all of those commands. The directions say to make 4 plots on one page. To do that, the subplot command indicates 2 rows of plots, 2 columns of plots, and plot number 1. That's what the 221 means. And then to make a second plot, 2 rows of plots, 2 columns of plots, and plot number 2, that's where it shows up. Made a mistake, so I fixed my mistake. And there's the second plot. As an example, 2 more plots you're asked to make. I'll now demonstrate how to make a coplot, how to plot 2 traces on one plot. This will be a dummy example. You won't be doing this. You'll be writing a similar one. I'll create a dummy variable called xx, and I'll just make it 2 times t, 2t, be a straight line with a slope of 2. And I'll plot that, coplot that on top of x, just as an example. Save it, run it. Now, the slope is too large, and so the original plot is buried in the line. So I'll make the slope smaller. so we can see the original trace. So there we go. That shows how to make two traces on one plot. Use the TI-89 to solve the differential equation and also plot the solution. Here is the TI-89 plot of the solution. The variables were changed. X was replaced by y and t was replaced by x in the differential equation. There is the original differential equation. With the change of variables, x becomes y and t becomes x. The boundary conditions also have to be stated. The initial position is 0 and the initial rate is 0. So I use the DE function and enter the differential equation y double prime plus 0.4 y prime plus 10y equals 1. And the initial boundary condition, the initial position is 0, and the initial rate is 0. The independent variable is x, the dependent variable is y, and when I enter that, the solution of the differential equation appears here. I can grab that solution, copy it, now open the function and paste it into the first function, then set the window parameters. X goes from 0 to 20, y goes from 0 to 0.2, and then graph that function. The Stanley method can also solve the differential equation, and the solution will have a slightly different form, but the Stanley solution will be the same as the TI-89 solution and also the same as the Simulink solution.